Thanks for the introduction. Hello, I'm Taobing from Peking University. I will talk about my work on private data manipulation in sponsor search auctions. This is joint work with Xiaotie Deng at Peking University and Tao Xiao at Shanghai Jiao Tong University. This work has appeared in this year's web conference. In a classical sponsor search auction, there's a seller or a search engine who sells a set of ad slots to a set of advertisers. When a user searches for something, for example hotel booking, an auction starts, and then the advertisers can buy ad slots from Google to display their ads. Different ad slots may have different quality, which means they have different probabilities of being clicked by a user. We assume the probability of being clicked is dependent only on the location of the ad slots, but do not depend on the content of the advertisements. When a user clicks an advertisement, the corresponding advertiser can obtain some value. But the seller Google doesn't know the values of buyers. Instead, the buyers submit a set of bids to Google. And given this set of bids, Google determines how to allocate ad slots to advertisers and determines how much money each advertiser should pay. This is formally described by two functions x and p, where x maps the bids to the allocation, and p determines the payment of buyers. Say the first slot is allocated to the first buyer and the second slot is allocated to the second buyer, and the buyers pay P1 and P2 and 0 respectively. Then the utility of a buyer is the quality of the ad slots times the value and minus the payment. And the sum of payment is the revenue of the seller. Then what do I mean by private data manipulation? In economics, there's a classical assumption, the Bayesian assumption, which says that in an auction, the values of buyers follow some prior distributions. Prior distributions mean that the buyers and the seller know the distributions before the auction starts. Here we use Fi to denote the distribution of buyer I's value, Vi. So the prior distribution of values, Fi's, are public information. They are known to all buyers and they are known to the seller. So the seller can design the auction based on the prior distributions. And in 1981, Roger Myerson, assuming that buyers' value distributions are known to the seller, proposed an auction that maximizes the seller's expected revenue, which is the expected sum of payments in the auction when the buyers bid their values and the values follow the prior distributions. At the same time, Myerson's auction is truthful, which means that the buyers have no incentive to deviate from bidding their value. So bidding BI that equals BI maximizes buyer I's expected utility. But there's a drawback of Myerson's auction, which is that the allocation X and the payment P depend not only on the bids, but also on the prior distribution of values. Mathematically, X and P takes both bids B and distributions F as inputs. Why do I say this is a drawback? Because in practice, the value distribution FIs are not public. They are private information of buyers. So FI is known only to buyer I, but not known to the seller. So the seller cannot design the auction based on the value distributions. So the seller cannot run Myerson's auction because Myerson's auction depends on value distributions. In fact, Wilson criticized Myerson's auction in 1987 by saying that in mechanism design, the mechanism designer should not use the prior distributions to design mechanism. But in sponsor search auction setting, things are a little bit different. Sponsor search auctions in practice are repeated. There are many interactions between the seller, Google, and the buyer, say Booking.com, because there are many users on the web. When a user searches for hotel booking, an auction starts. And when many users searches for hotel booking, many auctions are run, millions of times a day. So Google is able to collect many bids from the buyers. And if the bids are equal to the values, Google is able to collect many sample of values from buyers. After collecting many samples, Google is able to learn the value distribution of buyers. After learning the value distributions, Google is able to run the buyer's auction to maximize its expected revenue. However, it is not that easy for Google to learn the value distributions because bids may not be equal to the values. That is to say, buyers may have incentive to manipulate their bidding data. Here, manipulating bidding data simply means buyers submit bids that are different from their values. Why do buyers have the incentive to manipulate in truthful auction like Marston's auction? Because Marston's auction is truthful only when the value distribution it uses equal to the true value distribution of buyers. However, in this setting, the value distribution Marston's auction uses is determined from the samples provided by the buyers. When the buyers provide some bids that are not equal to their values, they essentially provide a false value distribution to Google. And then Google will run Marston's auction on this false distribution. And the allocation rule and payment rule are dependent on the false distribution. And maybe by carefully choosing the bidding strategy, buyers can submit a very good false distribution such that their expected utility increase compared to truthfully bidding. In fact, our work will show that because of this manipulation, Marston's auction is no longer truthful and no longer revenue maximizing. And we call this model private data manipulation model. Now we formally describe our private data manipulation game. In this game, there's a seller. The seller announces a prior dependent mechanism M. Prior dependence means that the allocation and payment of mechanism M depend on the prior distributions. So you can see that the X and P have two parameters. The first parameter is the bids, and the second parameter is the prior distributions. After the seller announces the mechanism, buyers choose some bidding strategies in response. Where SI is the strategy of buyer I, the strategy maps the buyer I's value to her bids. Mathematically, XI is a mapping between non-negative real numbers. But at the same time, the strategy SI is also a mapping between distributions. We use FI here to denote the manipulated distribution. The manipulated distribution is the distribution of bits. That is the distribution of SIVI, where the VI follows the true value distribution FI. And then this manipulated distribution FI heads are given to the seller. We assume that the seller has full information about the manipulated distribution, and then she runs the mechanism M with these manipulated distributions as prior distributions. That's the game, and we can write down the utility of a buyer. The utility of a buyer I is the expected allocation times the value minus the payment. Here the allocation Xi depends on the bits S of V and the manipulated distributions F hat. F hat means all the FIs. And also the payment PI depends on the bits and all the manipulated distributions. And again, the revenue of the seller is the expected sum of payments. The solution concept we consider is the Nash equilibrium. A strategy profile S is a Nash equilibrium if for each bidder I, SI maximizes I's utility over all possible strategies. Before presenting our results, we review another auction called Generalized First Price Auction, GFP for short, in the sponsor search auction setting. The allocation rule of GFP is as follows. The seller sorts the bids non-increasingly and sorts the S lot by their quality non-increasingly as well, and then allocate the best lot to the highest bidder and the second slot to the second bidder and the last lot to the last bidder. That's the allocation. And for the payment, each bidder pays her bid for each click. So the payment of bidder I is the allocation xi times the bids bi. We emphasize that the GFP is prior independent, which means that the allocation and payment do not depend on the prior distributions. They depend on bids only. Because of that, the private data manipulation game with GFP as the mechanism is the same as the classical Bayesian game. That is to say, if a strategy profile is a Nash equilibrium in the PDN game, then it is also a Nash equilibrium in the Bayesian game, and vice versa. Moreover, GFP is non-truthful. If a buyer has value VI and she bids VI, then her utility is 0. So she has the incentive to decrease her bid. Now I'm gonna present our results. Our main theorem shows that the private data manipulation game with Marston's auction as the mechanism is equivalent to the PDN game with GFP as the mechanism, which is of course equivalent to the Bayesian game of GFP. Formally, there is a bijection between the Nash equilibrium of the PDN game with Marston's auction as the mechanism and the Nash equilibrium of the PDN game with GFP as the mechanism, such that buyers have the same utility and the seller has the same revenue under the two corresponding Nash equilibria. This main theorem implies that Marston's auction is no longer truthful because the corresponding GFP is not truthful. And Marston's auction is not revenue maximizing because GFP is not. We can see that in the PDN model, learning is useless for the seller. Even if the seller uses the bidding history of buyers to reconstruct their value distributions, the strategic behavior of buyers makes the revenue of the seller decrease to the revenue in the Manila generalized first price auction. The generalized first price auction has allocation rule and payment rule that do not depend on prior distribution at all, so the seller doesn't need to learn the value distribution at all. Before presenting the proof, I will show you some other results. Our main theorem holds for general value distributions. As long as buyers have independent but probably non-identical value distributions, Marston's auction and GFP are equivalent under the PDN model. If buyers have independent and identical value distributions, then Marston's auction, GFP, and the VCG auction are all equivalent. Furthermore, if the IID value distribution satisfies some condition such that the generalized second price auction has symmetric Bayesian Nash equilibrium, then all these four auctions, Marston, GFP, VCG, and GSP, are equivalent. But we have some examples where the generalized second price auction doesn't have a symmetric Bayesian Nash equilibrium for some IID value distributions. We have those examples in our paper. For the second and third equivalences, we use the classical revenue equivalence theorem to prove them, and for our main theorem, I will show the proof next. We first review Marston's auction. Under the private data manipulation setting, the prior distributions are no longer the true value distributions. They are the manipulated distribution Fi hats. We define virtual value, denoted by phi I hat. The virtual values are defined on the manipulated distribution Fi hats. We use capital Fi to denote the cumulative distribution, and we use little f to denote the density function. The virtual value of beta I is defined as follows. Then for the allocation rule of Marston's auction, a Marston's auction should maximize the total virtual welfare, where the virtual welfare of beta I is her allocation xi times her virtual value phi I hat. In the sponsored search auction, because each S-lot can be allocated to at most one bidder, and each bidder can receive at most one slot. So in order to maximize the total virtual welfare, we need to sort the S-lots by their quality non-increasingly, and sort the bidders by their virtual values non-increasingly as well, and then allocate the slots to bidders one by one. By rearrangement inequality, we can show that this allocation maximizes the total virtual welfare. For the payment, The payment of master's auction can be characterized by the following lemma, which shows that the expected payment of bidder I equals her expected virtual welfare. So you can see that the purple part, the expected payment, equals to the expectation of allocation xi times her virtual value phi I hat. The second part of the proof is to analyze bidder I's utility in PDN game with master auction as the mechanism. By Marsden's payment identity, which says that the payment equals to the expected virtual welfare, we can write down bidder I's utility as follows. The utility is the allocation times the value minus the payment, and the payment can be replaced by virtual welfare. The purple part can be replaced by the red part. The red part is the virtual welfare, the allocation xi times bidder I's virtual value. Notice that this is the virtual value for S of V. V is the value of bidder I, and SI is the strategy of bidder I, which maps her value to bid. And then for the allocation rule of Marsden's auction, notice that in Marsden's auction, we sort the bidders by their virtual values non-increasingly and allocate the slots to bidders one by one. And in GFP, we sort the bidders non-increasingly by their bids. So if we regard the virtual values and the bids as the same, we can see that the Marsden's auction's allocation rule is exactly the allocation rule of GFP, where bids are replaced by virtual values. So we can replace the blue part by the green part and write the utility as follows. It is the expectation of allocation times the value minus virtual value, where the allocation is the GFP allocation with virtual values as bids. So this is exactly the utility in the GFP with the following bidding strategy. So we construct a bidding strategy, BIGFP, such that the bid of this bidding strategy equals to the virtual value of the Marsden strategy SI. On the other hand, for each bidding strategy in the GFP auction, we can construct a strategy in the Marsden auction such that the virtual value of the Marsden strategy equals to the bid of the GFP strategy. In this way, we can establish a bijection between the strategies in the two auctions such that the corresponding strategies have the same utility for each bidder I. That concludes the proof. Finally, I want to talk about some related works. There are some related works about the PDM model. Xiaotiedeng and his students study a PDM model where the value distributions and the bid distributions cannot be arbitrary distributions. They can be chosen only from some special family of distributions. They found that the Marsden's auction is not truthful. Later, Tang and Zheng in their EC18 paper studied a special case of PDN game where there's only one item for sale, so there's only one S slot. They concluded that the Marsden's auction and the first price auctions are equivalent. So their work is a special case of our work. The PDN model has an unrealistic assumption, that is the seller knows the full distribution of buyers' bids. There are many works that study incentive-aware learning without this assumption. So the seller is trying to learn buyers' value distribution and the buyers bid strategically in response to that. But the seller cannot observe the full bidding distribution of buyers. The last line of related works that I want to mention is about Google's switch to first price auction. Some works explain that switch, and our work shows that Marsden's auction is equivalent to first price auction, so that can be one reason for that switch. But there are some other works, 1.20 paper, say that Google switched to first price auction because there are many competing sellers on the internet. When there are more than one seller, then choosing first price auction instead of other auctions is a natural equilibrium for the competing sellers. So considering multiple sellers is an open direction for our PDM model. That's all. Thank you. Feel free to ask questions.
Okay, it's great talk. We have one question. That's what's the assumed learning strategy of the buyers?
What's the learning strategy?
Assumed learning strategy of sellers? Okay.
Yeah, in this model or in this paper, we assume the seller is using the milestones auction. So the seller collects some samples and then run the milestones auction on the uniform distribution over these samples. So basically, this is the empirical risk minimization learning algorithm.
Okay, second question. How will conclusion change if there are only a few of the buyers are malicious?
Only a few of the buyers are malicious. Yeah, that's an interesting question. So actually, I don't know. Our conclusion says that there's a mapping between the strategies of the buyers in the first price auction and the milestone auction under the PDN game. So this conclusion still holds if there's only a small set of buyers who are strategic. So if some buyers are truthful and some buyers are strategic, then we can map the strategies of the strategic buyers, map their strategies between the first price auction and the milestones auction. So in order to analyze their bidding behavior in the milestones auction, we only need to analyze the first price auction. So the problem then becomes what happens in the first price auction if only a fraction of buyers are strategic. So, but in order to answer that question is difficult because even if you assume all buyers are strategic, then what happens in the first price auction? That's unclear. So you want to analyze the Nash equilibrium, right? Nash equilibrium in the first price auction when all buyers are strategic, but this question is open. So whether this Nash equilibrium exists or whether this Nash equilibrium is unique, if it exists, is still unknown.
Okay, right. Third question. What is the cost for a buyer to manipulate the value distribution?
The cost for the buyers to manipulate the value distributions. We didn't model the cost in our model. So our model assumes that buyers and seller are playing many auctions and somehow they converge to a stable state. So under the stable states, their strategies are fixed. So buyer strategy is fixed. And so we are considering the final state of the dynamics and we conclude and we study the property of these final states. And we didn't study the early stage of these dynamics.
And the last question from your audience is, making manipulation to fool the seller is costly. For instance, every time when the buyer bids falsely, she will gain less. So after several rounds of SSA, it may be less appealing to counterfeit her value distribution. Will the conclusion change if we consider a number of repeated PDM auctions?
Yes, this question is similar to the last one, which says that manipulating, bidding truthfully in truthful auction is costly. So if they play many rounds, at first they suffer some loss, and maybe later they obtain higher utility. So you're asking what happened if I assume that you want to know what happened in the finite number of rounds of repeated auctions. So auctions are repeated, but there are finite number of rounds. There are not infinite number of rounds. Then what happened? So many papers are working on that. I can give you one example. For example, if there's only one bidder and one seller, and the one bidder and one seller plays finally number of rounds, and you can see that the buyer can always bid 0, and if she always bids 0, then at first she suffers some loss, but after a short time, the seller learns that the buyer's value is 0. It's a false value, but the seller learns that her value is 0. So the seller will set the reserve price to be 0. And then, yeah, you can see that at first the seller suffers some loss, a small loss, but maybe after some round, like square root of t rounds, then in all the remaining rounds, the reserve price is 0. Then the buyer can obtain many utilities.
Okay. Thank you for answering, and we can end our talk now, and the next talk will start in 3 minutes.
Thank you.